Hi everyone, this is Sharan here. Welcome to my channel. Today in this video, we are going to see about the various metrics that can be used to evaluate the performance of an regression model. There are various metrics. We will be going through each one of them. We will be going through the mathematical formula behind them or the concept behind them. Also, we will be going through how to implement those metrics using a simple Excel sheet in order to understand better like what is happening across each one of them, and finally how to implement those metrics using Python, so that if you are building a regression model, you can easily refer to these metrics and then implement those to see how good or how is the performance of your regression model. So let's get into the topic and then see what are all those metrics one by one and the concept behind it. So the first one is the R squared for a regression. So this is goodness of fit measure. So this is a measure that is used to see how much of the variance that is present in the dependent variable that is explained by the independent variables. So when I say dependent variable, it is the variable that we are trying to predict. So how much of the variance present in the variable that we are trying to predict is explained by the various independent variable, which is the various inputs that we pass to the model. So this measure generally will range from 0 to 1. It can of course in some cases go in negative as well, but generally it ranges from 0 to 1. When we have 1, it means that the 100% variance of an dependent variable is being explained by the independent variable, which means that our model is 100% accurate. So whatever we are predicting, it exactly matches with the actual value. So that's when the R square value will reach 1. When we have it as 0 or a lower R squared value, it simply means that whatever we are trying to predict is nowhere close to the actual value. So coming to the important point, so does it mean that having a high R square value always means that the model is extremely good? No, so that's not the case. So all these measures that we are coming up is based on the training data set that we have. So if a model has an overfit, for example, like the model is performing extremely well for the training data set, so what would happen is we will have extremely high R squared value. Whereas when we put the same model into test, so what might happen is the accuracy of the model might not be as good as as we expect based on the R squared value. Similarly, when we have a lower R squared value, it doesn't really mean that the model is going to perform really bad on a test data set. It just means that for the training data set, the model was not good enough. So generally speaking, so if you have a lower R squared value, it means that even on a training data set, the model is not able to perform really good. So which means that it's most likely to fail on a test data set as well. So generally, that's what it means. But it can't be taken as a rule. Whenever the R square value is low, it can't be taken as the model is extremely bad. In some cases, for example, when we are trying to predict an human behavior, when a particular person might buy or what a particular person might do on a website, whatever it might be, which is related to an human human behavior, so which is very unpredictable. So in those cases, it is expected to have a slightly lower R squared value. So depending upon the scenario, you can pick up an value, you can set a threshold and then go with it. So there is no fixed threshold for regression problems in general. Depending upon the problem that you are trying to solve, you can maybe take a particular value, a particular R squared value as acceptable or not. So that is the R squared for regression. So now moving on to the next one. So we will be going through the implementation of R squared for regression, and I will also show you what is the mathematical formula, how we arrive at R squared value. But for now, let's go forward. So the next one is mean squared error. So as you see on my screen, so this is the formula for mean squared error. So what we do is we take the actual y value, we take the predicted y value. So y bar that you see is the predicted y value. So we take a square of it, we do the summation for all the observations, and then we divide by the number of observation. So this is the mean squared error. When we use the mean squared error, obviously what is going to happen is the scale is going to be huge. whenever the difference is larger, the penalty is going to be much larger, because what we are doing is we are taking the square of the error. So it's going to be much larger in scale. So the next one is root mean squared error. So root mean squared error is very similar to mean squared error, but what happens is towards the end we take a square root of it. So what we are trying to do is we are trying to bring down the scale of the measure so that it will be in line with the scale of the observations that we have. So it can be comparable. So root mean squared error is more comparable with the actual values, I would say. The next one is mean absolute error. So in this case, what we are trying to do is we are just trying to take the difference between the actual value as well as the predicted value and take the absolute of it, which means that modulus of it. So even if it is negative or positive, it doesn't matter. Like we add up all of it, we take a modulus of it, and then we add all of it and then we divide it by the number of observation to see how much is the deviation. So this value will also be very much in line with the actual observation, like the scale would be very similar. So it is comparable, unlike the mean squared error, so where the scale would be much larger and it's not comparable. Here in this case, it's much more comparable. So these are some of the measures, the metrics that can be used to measure the performance of the model. So now what we will do is we will just go back to an Excel to see how these metrics work. Coming to the Excel sheet, so as you see on my screen, what we have is we have the y original, the y observed value. We have the y predicted value, what we are predicting, what our model is predicting. And we have the third column, which is the y original minus the y predicted. What is the difference between both of them? And the fourth column is square of it. So why we are doing the square? Because sometimes the difference between the y original and the y predicted might be positive. In some cases, it might be negative. When we square it, what happens is it always becomes positive. So it is easy to measure the actual deviation of our prediction as compared to the actual observation. So that's why we always take a square, we add it, and then we divide it by the number of observation. So the first one, as you see on my screen, is the mean squared error. So here what we are trying to do is we are trying to add up all the values that is present here, which is the square of the difference between the original as well as the predicted value, and then we divide it by the number of observations. So as you see here, the value is 3.8. So here in this case, the scale, the value 3.8 is not actually comparable with the actual values. So if you see here, the difference is, in each of these cases, the difference is 2, 1, and in one case, the difference is 3. Whereas the mean squared error, the value that we are getting is 3.8. So as you see, it is not comparable because mean squared error will be always on the larger scale. And whenever the deviation grows, whenever we have a higher deviation, the penalty would be much more higher because we are squaring it. So the second one is root mean squared error. So here in this case, what we are doing is we are taking the mean squared error and then we are taking the square root of it. It's as simple as it. So now what happens is we are able to bring down the scale. So now what we are getting is we are getting the value of 1.94 here, as you see. So this is more comparable with the values that we have. So as you see, we always go on average off by 2 values. Whenever the actual observation is maybe 10, we are predicting it as 12. So we always go on an average maybe closer to 2 values off from the actual value. So the root mean square value that we are getting is almost in scale, I would say, with the deviation that we have with the prediction. So somewhat comparable with what we have. The third one is the mean absolute error. So here in this case, what we are doing is we are taking the difference between the y original and the y predicted, and we are taking the absolute of it, we are taking the modulus of it. So if it is negative, we convert it into positive. If it is positive, it remains positive. And then we add all of it and then divide it by the number of observation. So this will also be in scale with, will be comparable with the values that we have. So as you see here, what we are getting is we are getting 1.8 here. So essentially what we are doing is we are taking modulus of each of these values. We are adding all of it. So here in this case, if we add all of it, we will be getting 9. So 9 divided by 5, which is the number of observation, will be equal to 1.8. So that's how we get mean absolute error here. So that's how each of these measures would work. So now coming to the Python implementation, if you are building an regression model and you want to measure how good or how bad your model is performing. So how can we implement it? So what I'm going to do is I'm going to show you a simple example here. So I'm not going into the details of how the model is being built. So let's take it for granted that we have built a model, we have made the prediction, and then we are going to focus on how to measure the accuracy of the model. And I'm going to execute the packages. So if you have any questions regarding these scripts, if you want to reuse it, I will be uploading all the scripts to my Git repository. So you can take a copy of it and then you can work on it. So now this is like the diabetes data set, which we have used for a few times in the past while learning like few regression algorithms. So I'm just going to I'm just going to load those data, and I'm just going to execute each of these. Like if you have any questions like how to build a regression model, what I will do is I will provide a link in the description where you can go and learn like how this model is being built. But for now, we are going to take it as granted. We are going to use it. So I'm converting this into a data frame, and this is what our data set would look like. And I'm going to separate, like pick up the target value, the value that we are going to predict, and I'm using this to split it into a training data set and test data set. And so here comes the model prediction, like a predictive model. So we are using linear regression in this case, and I'm going to use fit to train the model, and so I'm going to use model.store. So the output that we get when we use model.store, especially when using the regression model, so this is the R-squared value. So as I said, so here in this case the value is 0.33. So if the value is closer to 1, it means that our model is 100% accurate. So here in this case it's not 100% accurate. It's not really bad too, right? It's okay, like a 0.33, it's okay. So this is how this is the formula for the R-squared value. So what happens is it's y minus u by v, where u is, so it's the square of like the y true value, like the square of the difference between the y actual value and the y predicted value. So then what we do is we take a sum of all of them, and the denominator v is nothing but y actual value and then difference with respect to the mean of y. So like for each one of, like for all the observations, like we calculate these values, and based on this particular formula here we get the R-squared value. So here in this case the R-squared value is 0.33. That's the mathematics behind the R-squared metric. So the next one is we are just seeing the coefficient for this regression model, and we are reading the intercept, and this is what our model is predicting, the output of it. So this is an important column which we will be using to measure the performance of the model. So this is the column where we have predicted as well as actual. These two will be the column that we will be using to implement all the different metrics that we have just covered. So the first one is mean squared error. So when if you are using sklearn, so what you can do is you can import the metrics and you can use mean squared error. So it's very simple. Like you can use the mean squared error as a function and then pass on both the like actual value as well as the predicted value, and then it gives you the results. So if I run here, so this is the value of our prediction of our performance of a predictive model. So it's 3424. So as I mentioned, the mean squared error will be definitely on a larger scale. Whenever the difference is higher, the penalty will also be much higher. So you can always expect that the value for mean squared error will be much higher. So no need to worry about it. The next one is root mean squared error. So here in this case, what we will be doing is we'll be taking the square root of the value. So what we are doing is we are not using a separate function of it. We are just using the square root functionality, and we are just using the mean squared error because that's what it is. And let me execute it, and then the value is 58.51. So now if you see, the values are comparable. Like it's almost very closer to the scale of the actual observations that we have. What's the actual difference between them? So if you see some of these values, right, the difference will be more or less similar to, on average, it will be similar to the root mean squared error that we are getting. And the final one is mean absolute error. So as part of sklearn metrics again, so mean absolute error is also available as an functionality that you can directly use. So what I'm doing is I'm using mean absolute error and then passing on the both actual value as well as the predicted value, so that the this particular function can give us the measure for mean absolute error. So when I executed this, so the value is 46.14. so almost close to the root mean squared error. So almost like on scale with the actual values that we have. So these are all the various measure, and then how to implement it. So as you see, implementing some of these measures are very simple. They are already part of stlearn package. So if you use stlearn.metrics, all these comes up as an functionality that is available already to you. So all you need to do is you need to just use the measure, the right measure which you want to pick, and pass on both the actual value as well as the predicted value, so that the measures the output will be available to you. Coming back to the presentation here, so now what is the recommendation? So we saw about various metrics that can be used to measure the performance in case of an regression model, but when to use what? So as you see on my screen, R squared measure is good to explain how good the model is. So this is a good measure in order to explain to a business, because what we are able to get is we are able to explain the variance, we are able to measure how much variance of the column that we are trying to predict is explained by the various inputs that we are passing by the model. So the next one is, as I said, the mean squared error. The values will always be on a larger scale. Whenever the difference is larger, the penalty is also going to be much larger. So in most cases, it's not preferable to use mean squared error. So even if you use mean squared error, don't go with the scale. Even if the value that you are getting is quite large, it is absolutely fine. The next one is root mean squared error. It's very easy to interpret. The scale is also very similar to the actual observations that we have. In majority of the problems, in majority of the regression problem, this is a metric. This is extremely good metric to measure the performance of a model. So if you see a lot of title competitions, in most of the notebooks that you would find, in case of regression problems, root mean squared error would be the metric that will be used generally in order to measure the performance of the model. So if you want to stick with the majority, you can simply go with root mean squared error. If you don't want to maybe spend time in choosing the ideal metric for your use case. And mean absolute error, it treats all the errors equally. It's also very much in line with the scale of the actual observations that we have, but I would say it is preferable to maybe stick with root mean squared error. Yeah, so that's it for now. So what we have covered today is we have covered what are all the different metrics that can be used to measure the performance of a regression model. We have seen the concept, the mathematical formula behind it, and how it works using an Excel sheet. Also how to implement it using the Python. So using Python, it becomes very simple. It comes as part of stlearn package. So with just one line of code, we will be able to measure the performance of the model. So that's it for now. I hope you would have understood or learned something new today. If you have learned something new, or if you find this interesting, please give a thumbs up and subscribe to my channel. If you think this might be helpful to any of your friends, please share it with them as well. So that's it for now. We will see you in the next session. Thank you. Bye.